Bem-vindos to one more episode of the Type Theory for All podcast. This is your host, Pedro Abreu, and in today's episode I interview Anupam Das. I met him as a lecturer at the Midlands Graduate Summer School. He was teaching some mind-blowing stuff about natural deduction, sequent calculus, cut elimination, so I decided to invite him to talk more about it. So join us in this amazing conversation on the historical perspective of how logic and proof theory, as we know today, came about in the 30s, the differences between natural deduction and sequent calculus, cut elimination, and so much more. Let's get into it! Ladies and gentlemen, welcome to one more episode. Today with me, I have Anupam Das, and he is a lecturer in the School of Computer Science at the University of Birmingham in the UK. He was a Marie Sklodowska-Curie Fellow at the University of Copenhagen. He has postdocs at École Normale Supérieure de Lyon and École Polytechnique. He's done his PhD at the University of Bath in 2013 and have a master's in mathematics in the University of Oxford in 2010. Thank you so much for joining us today, Anupam, and welcome.
It's a pleasure, Pedro. I'm happy to be here.
I actually have a super random question, but which department exactly do you sit in Birmingham?
As you said, I am in the School of Computer Science. It's a good question because my background was really in mathematics. And I have this confession that I say to everyone who asks me that I still don't really know how to program. So I never learned programming. So I'm probably one of the few lecturers in computer science, few people who made it to lecture in computer science without knowing how to program. But there are logicians in other departments at Birmingham, which makes it very interesting.
Right. I'm always kind of curious. Like that, the reason why I ask this question is because you actually work more in the, logic side of computer science, right? So you could fit in philosophy department, you could fit in mathematics department, and you can fit in computer science department too, right?
Yeah, I actually started out studying mathematics and philosophy before I transitioned into mathematics. But yeah, I think in what I do in proof theory, you do see people from all of these different disciplines at play, and they just, they have similar technical tools in play, but they study slightly different questions. So, you see proof theorists in philosophy departments, you see proof theorists in mathematics departments, and so on.
Right. That is really cool. And the reason why I invited you for to be here today is because we met at the Midlands Summer School, and I have such an amazing time with your lecturers. And I was thinking we could make an episode just to talk about logics. Like talk about what was going on. Like you spent a lot of time talking about cut elimination, talking about how Gentzen was a person ahead of his time, and all of that. And I'm like, man, we need to talk about proof theory. There's so much cool stuff happening there. So how about we start off by you giving us a little historical background of, right before Turing and Church come up with lambda calculus, there is a lot happening in the field of mathematics, of logic. Why don't you give us a little bit of taste of what is going on then?
Well, that's quite an ominous question, but you did warn me in advance that you'd ask me this, so I prepared something I'll say. So the first thing I'll say is, for details of historical stuff, please just read something that's got citations, like the Stanford Encyclopedia of Philosophy is very good for this. But I think maybe the answer that you're looking for is my personal viewpoint of what things were significant and what things weren't.
Oh yeah, I should probably warn the listener by now that everything here should be taken as personal points of views, and don't take our word as the final proof and perspective of anything, right?
Yeah, and in particular, there's just so many good resources to actually learn for yourself about the actual facts. But I can tell you what I thought was significant, and maybe I'm biased because of the way I learned it. So when I was a first year undergraduate doing mathematics and philosophy, I remember reading Frege's Foundations of Arithmetic and learning about that whole historical episode. And it somewhat, really cemented my viewpoint of the history of logic. So in broad terms, the 19th century was a story of this reemergence of foundations and logic and wanting to understand what mathematics was founded upon, because, all of this calculus and analysis that had been developed was all very wishy-washy. There was this idea of infinitesimals, dy by dx, this kind of stuff. And so people wanted to know what this stuff was founded upon. And so for me, to this end, the first serious attempt, the first serious piece of work that tried to create the foundations of arithmetic was Frege's foundations of arithmetic, his Begriffsschrift. And his idea was quite simple. He wanted mathematics to be seen as an extension of pure logic. So he thought that the ontological statement of mathematical truth was the same as the status of logical truth.
What does ontological means here?
It means, so for example, so let's not use fancy words. So let's say when we say a scientific truth, the status of that truth is maybe different from the status of a mathematical truth. So when I say that when I let go of a ball, it will hit the floor, the status of that true statement is different from the status of the statement 2 + 2 = 4, or all bachelors are unmarried. Because the second two are somehow true by virtue of what they're saying. They're almost analytic truths, what they call it. Whereas the fact the ball will hit the floor, well, to be fair, I don't actually know it's going to hit the floor, right? All I know is that it's happened in the past. And by scientific induction, I'm assuming it's going to happen again. So in some sense, we should have less confidence in that statement than this statement that 2 + 2 = 4. So the key thing was that Frege thought that the status of 2 + 2 = 4, and more generally, much more complex statements like Fermat's last theorem and things like this, were the same as the status of statements like all bachelors are unmarried. He thought it was just pure logic. And so he developed his foundations, and this was, I think, the first example of a quantified logical system that was well behaved. So he created this calculus. Before him, there were people like Boole and Peirce, who had developed systems of Boolean logic or propositional logic. But I think Frege was the first to give a meaningful treatment of the quantifiers. And he thought he had a good definition of number, a good theory, and he was able to treat arithmetic as an extension of pure logic. But of course, then the big blow came, right, when Russell provided Russell's paradox, which was displayed an inconsistency in Frege's framework. And that inconsistency is now what we might term naive comprehension, the fact that we cannot have naive comprehension consistently in a theory, which was Frege's basic principle number 5.
Right. So by naive comprehension, you basically mean that the idea of the set cannot contain itself or talk about itself, something along those lines.
Yeah. So more generally, given a property P, you can't take the set of all things satisfying P. Not in general, because otherwise you would be able to formulate Russell's paradox, which takes the set of all elements that are not elements of themselves, and that induces Russell's paradox. And so that for me was the first big significant thing that okay, we want foundations, but actually this is a bit of you have to be very delicate with them because you can make errors, and it's very easy to get inconsistent theories. And that's really what gave rise to Hilbert's program. So Hilbert, the beginning of the 20th century, I believe Russell's paradox was already known at this point, asked for an actual foundations that was consistent. And because of the problem of Russell's paradox, asked, moreover, for a proof of its consistency within a theory that was so simple that no one could doubt its consistency. So before Frege proposed foundations of arithmetic, and its consistency was refuted by Russell. So now Hilbert was asking, okay, we want our foundations, but we moreover want a proof of the consistency of these foundations within only using reasoning that none of us can dispute. So it must be an incredibly simple theory. And, this led to Russell and Whitehead's Principia Mathematica. This was, a sort of typed framework where Russell's paradox was avoided by typing sets as they increased in their abstraction complexity. And then, of course, the big blow to Hilbert's program was then Gödel's incompleteness theorems, because he said that not only can you not prove the consistency of Principia Mathematica or Piano arithmetic within a simple theory, you can't even prove it within itself. You must use more complex axioms to prove the consistency. And in a sense, like if those results closed the book on, say, mathematical logic, they sort of opened the way for computational logic, because around the same time, these sort of techniques, these diagonalization techniques, for example, played a huge role in the foundations of computer science. So, this was the same sort of technique that Turing used for his undecidability of the halting problem. And, results like this from the 30s, of course, they have, we have reflections of that nowadays. Nowadays, when we talk about debugging and verification, these all sort of like trace their roots down to these sort of foundational results. So I see the 30s as really the pivotal point where Okay, it's unfair to say mathematical logic died, but let's say foundations sort of had hit their peak, and computational logic was just beginning. In the next 50 years, I think was a story of the rise of computational logic.
Right, right. And where does Gensen comes into play there?
That's a good question. So around the same time that Turing and of course Church and Kleene came up with their models of computation, Gensen came up with his systems of proof. So until this time, the only sort of systems of reasoning we had were these axiomatic systems attributed variously to Frege, Hilbert, Dedekind, and Ackermann. And these gave us ways of reasoning. And of course, Gödel did prove the completeness theorem for these systems. But we had no way to actually manipulate proof. We had no way to actually, do some proof theory with them. And so Gensen introduced natural deduction and the sequent calculus. And if Gödel's results, his incompleteness theorems, were kind of a pessimistic result, they were saying that there are things that we cannot prove and we can't even prove our own consistency and that sort of thing, then Gensen's results are much more optimistic because he proved his famous Hauptsatz, the cut elimination theorem. And this states that, of the things we can prove in pure logic, not arithmetic, but at least in pure logic, at the very least, we can prove them without making any guesses. We don't have to make any clever mathematical guesses in order to prove them. We can just proceed in a sort of deterministic fashion, well, almost deterministic fashion, to prove theorems of pure logic, only using concepts found in the conclusion of the proof itself, the theorem that you're trying to prove.
Is that what they call the analytic proofs? Is that
Precisely, yeah.
related?
So when people say analytic proof, they mean proofs that satisfy the subformula. They usually mean proofs that satisfy the subformula property. And this is a consequence of Gensen's cut elimination and normalization theorems for sequent calculus and natural deduction, respectively. And I think, like I said, at the time, this was, we had the inception of something like computability theory because of the work of Turing, but also of Kleene and Church. And we, at the same time, had the inception of modern proof theory because until then, people weren't doing proof theory; they were just doing formalized reasoning. And so the 30s was really, the birth of many areas. I mean, you could also argue it was the birth of model theory because, Tarski had done his work, Gödel had done his completeness theorems, and, Tarski's undefinability of truth came in, and the birth of modern model theory probably was around the 30s. Maybe I could rephrase my previous statement as the death of modern logic as saying the death of set theory, maybe. Of course, a lot of set theory was done, but that's pretty much what people were doing, right? I mean,
Right.
Maybe I should also give a lot of credit to Cantor in the 1880s, I want to say.
Right.
Because,
right.
Of course, his diagonal argument has been pervasive throughout logic, computation, everything. And so
That's where everything actually started, right? That was when we were like,
right.
oh, wow, there's actually a lot more happening here than we thought, right?
Yeah, I mean, people didn't know about multiple infinities, right? So in Cantor's work originally was just to mathematically prove that there were different sorts of infinity, infinities that were not equinumerous. And people just didn't know that until the 1880s, 1890s.
And I find absolutely fascinating the fact that he was actually, nobody actually kind of like believed him. They could see his proofs and they could not disprove what Cantor
I
has
didn't know
proved,
that. So no one believed what he was saying?
Nobody, yeah, and he actually died in a hospitium, like in a sanatorium.
I think I only know that from Logicomics, actually, and I'm more wary of how accurate Logicomics is.
Well, I don't know if he was probably not put there because of like his mathematical stuff. There was most likely other stuff happening, but people just didn't believe his proofs. Like he could see that there is this multiple infinities, but nobody actually could make sense at that time. So he was a lot ahead of their time in the 80s, right? And definitely set the ground for what was happening here in the 1930s, which we're talking about. Now let's go back a little bit on what you were saying about said something along the lines of undefinability of truth. I'd like to go back there again. This is new to me. What were you saying there? Tarski's model theory.
So this is in the world of arithmetized mathematics. So you have to imagine that to understand undefinability of truth, we're in a setting where coding now exists. So pre 1930s, people didn't really think of coding. But then, the idea of coding became more and more relevant throughout the 20s, with recursive function theory starting to appear.
By coding, you mean using another language to encode something else, or coding as like programs and algorithms?
No, I mean encoding things as natural numbers or binary
Right.
strings.
The same idea that Godel used in his proof, right? Encoding as
Precisely. So the
coding
idea
numbers,
that
right?
you can have interplay between a program and its code. You can feed the code to the program itself. So the program takes maybe a natural number as input, but it itself can be seen as a natural number because it has code. So this idea of playing with coding now exists. It's in the setting, and Tarski wanted to use this idea to talk about truth. So he said, "Look, I want a predicate, a formal symbol of a language that takes as inputs codes of sentences and evaluates whether the sentence is true or not." But of course, because of Gödel's diagonal lemma, well, I should say, I don't know if Gödel actually called it a diagonal. Because of his first incomplete, the techniques used to prove his first incompleteness theorem, no such predicate can exist. There is no first order formula in the language of arithmetic that can express this T predicate for truth. Because otherwise, by the diagonal lemma, you could express the sentence, "This sentence is not true," which would have no consistent truth value. So Tarski, this is usually attributed to Tarski, but as far as I know, I think this is really a consequence of Gödel's theorems. But Tarski was the one who maybe developed the ideas in a sequence of papers, I think written in Polish even. But yeah, when we say Tarski's undefinability of truth, we mean that there is no arithmetical formula that accepts just the true formulas as the codes of true formulas.
Right, right. Seems very similar to what Turing was doing with his universal Turing machine, right? In a way.
Yes, it is. You're quite right. But it's a negative result, right? It says there's no universal arithmetical property. So yeah, you can see this. So truth predicates and universality are just two sides of the same coin. So what does universal Turing machine say? It means there is a universal sigma 1 predicate, right? So sigma 1 means you have an existential quantifier and then a recursive matrix. And we have a universal sigma 1 predicate. We also have a universal sigma 2 predicate and a universal sigma 3 predicate, and so on and so on and so on. What we don't have is a universal predicate for them all at the same time. Not that it is self-arithmetical. So the set of arithmetical truths somehow doesn't form a nice class of languages because it has no universal problem.
Right, right. That is absolutely fantastic. Do you want to give a brief introduction about the sigma predicates you're talking about? Because when we were talking on the summer school, I think you gave me a brief idea of this hierarchy of proof systems. I believe this is what you're talking about here.
There's a hierarchy of formulas here. So this is really kind of a descriptive set theory stuff. So it's just, so if you take the Turing machines and take the halting problem for that, this ends up being what's called a sigma 1 property, because if you look at the way to state that, the statement is there is a time bound such that this machine will terminate within that bound and accept. So you can, if you think of the halting problem for Turing machines, you can write that down as an existential property, existential arithmetical property, right? You can say there exists a time bound such that this machine will terminate within that time and accept, right? So the latter part, the fact that to terminate within some time and accept, that's a recursive property. You just run the machine until that time bound. But whether the time bound exists or not is the thing that's hard to establish. And it's called sigma 1. Well, the sigma just means you have an exists at the front, and the 1 just means that's the only quantifier you have in front of a recursive matrix. And then this arithmetical hierarchy, you can build up on top of that by just alternating quantifiers.
And this gives you more expressibility in a sense?
Yes, provably. There are diagonal problems that separate each level of the hierarchy. But nonetheless, each level of the hierarchy has a universal problem. But the union of the hierarchy, which is just all arithmetical formulas, all arithmetical predicates, has no universal problem, which is the same as saying it has no truth predicate.
Oh, so that's where TARS comes in.
Exactly. So you can see Tarski's results, or de Gödel's results even, in a computational side. So, if you're a philosopher, you call them truth predicates. If you're a computer scientist, you call it a universal problem, right? It's really two sides of the same coin.
No, you also mentioned before this that when Gensen came in and gave a more algorithmic approach to logic, how was it done before that?
I'm not quite sure how to respond to this, but maybe I'll reiterate that the first time we could actually talk about proof rather than provability was when Gentzen introduced his systems. So until now, we were talking about things that we could prove. So we had an axiomatic system. We knew that the things that we could prove were closed under, modus ponens and other rules of inference. But we didn't really know how to study a proof itself and see structural properties within the proof. And you mentioned algorithmic approach. Well, we never had ways to, when I talk about manipulating proofs, we never had ways to put them into normal forms. And that's what Gentzen contributed. In his sequent calculus and his natural deduction, he most famously described a notion of normal form of a proof, and his cut elimination theorem gives us a normal form. And of course, what's amazing about that is many years later, the works of Curry and Howard gave us ways to see these normalization processes, namely for natural deduction, as computation itself. But by analogy with the simply typed lambda calculus. And so, this was, while proof theory and maybe computability theory were quite separated at this time, they both kind of found their roots in the 30s. It turned out that the developments were actually fundamentally intertwined by the Curry-Howard-Lambert correspondence.
Right, and you're saying that you can put that church and clean using normalization in the lambda calculus very closely tied to cut elimination. It basically means that cut elimination itself is close tied to the notion of termination of programs, right?
That's a good viewpoint. So firstly, I should say it's related to normalization in natural deduction rather than cut elimination per se. There are ways to see typed calculi related to sequent calculus, but that's much more modern. Yeah, so in the way that simple typing or a type system can guarantee termination of a program, the termination theorem for normalization in natural deduction has the same content, right? It says the same thing. It says that if you've got a class of proofs or a class of terms in this system, then you determine a well-defined functional.
So what's the difference here between natural deduction and sequent calculus?
I'm not sure what level I should address that in. This is a whiteboard style question, right? Gentzen first introduced natural deduction. I believe this was the first system he wanted to introduce because for him it was, as the title suggests, it was natural, and he thought this reflects how we actually do reasoning, in everyday mathematics. And for him, he thought this was really the one true system. So natural deduction has rules like, if you've got A and B, then you can infer A. If you've got A, then you can infer A or B. And those two rules are sort of dual to each other. And actually, every connective in natural deduction has a so-called introduction rule and a so-called elimination rule. So for conjunction, I just told you the elimination rule. It was from A and B, you can infer A. But the introduction rule is from a proof of A and from a proof of B, you can infer A and B. And you can think of these from the Curry-Howard correspondence point of view. You can think of the introduction and elimination rules as constructors and destructors, respectively. So in a type system, you have constructors, and these constructors just correspond to the introduction rules in a natural deduction system, and the destructors correspond to the elimination rules. So implication is probably the most interesting one. Implication says that if you've got a proof of A and a proof of A implies B, then you can infer B. And what does that mean on the other side of the Curry-Howard-Lambert correspondence? Well, this is just application, right? So you've got a function of type A implies A arrow B, and you've got an argument of type A, and so the constructor it's just the application constructor. Right? You apply the function f to the argument argument B. I can't remember exactly what I said there, but the second argument. So given all that, and given all this nice stuff, well, Gentzen wasn't aware of the Curry-Howard correspondence at the time, as far as we know. Given this nice sort of correspondence, why have sequent calculus? Well, from Gentzen's point of view, he was unable to prove things about natural deduction that he really, really wanted to prove. And my understanding of this is that this is namely the normalization theorem for classical natural deduction. So there's an interesting anecdote, actually. My understanding is that for many decades, we believe that he was unable to prove, we did not prove normalization for either intuitionistic or classical natural deduction. And the story was that he developed the sequent calculus in order to prove this result. So you can do a little detour. You can take a natural deduction proof. You can translate it to the sequent calculus. Then you can do this little black box cut elimination technique, which I haven't yet mentioned much about. But then the cool thing is, once you applied cut elimination, you end up with a cut-free proof. And from here, you can translate back to natural deduction, and you'll get what's called a normal natural deduction proof. So this is a natural deduction proof without any detours. So you don't have alternations of introduction and elimination rules. And this was why Gentzen, the story is, this is why Gentzen introduced the sequent calculus in the first place, because for him, it was a roundabout way of showing the normalization theorem for natural deduction. Now, as it happens, I'm not completely sure of all the details here, but I believe it was Jan van Plato who a couple of decades ago, I think, found some notes, some memoirs of Gentzen. And it turns out that Gentzen actually did prove the normalization theorem for intuitionistic natural deduction. But I think he declares that he was unable to do so for classical natural deduction. And actually it's for that reason that he developed the sequent calculus. So he actually did have a lot of results under his belt at this time. So it's an interesting story, but that's why he developed the sequent calculus. So I haven't answered your question though. What is the sequent calculus then? Well, it's based upon a simple idea, which is instead of having introduction and elimination rules, we kind of flip the derivation on it by 90 degrees. We have explicit listing of hypotheses. So instead of introduction and elimination, we now have left and right. So elimination rules become introduction rules on the left, and introduction rules become introduction rules on the right. But there's one more key thing which allows us to talk about which allows us to get a normal form, which is to bring duality to the forefront. So deduction, when you have explicit listing of hypotheses in natural deduction, you have a set of hypotheses entails a single formula. And then for classical logic, for example, you might have an elimination rule, which is something like if you can derive not A, then you can infer A. But this is not what happens in the sequent calculus. Instead, in the sequent calculus, we have a duality between the left-hand side and the right-hand side. We can have many formulas on the left, which are the hypotheses, but we can have many formulas on the right too. And if the left-hand side is interpreted as a conjunction of hypotheses, and the right-hand side is interpreted as a disjunction of conclusions. And that De Morgan duality between conjunction and disjunction is really one of the key features of the classical sequent calculus that makes its proof theory quite well behaved. And that's the thing that's sort of missing in natural deduction. We don't have that good account of duality.
So this simplifies the meta-theoretical proofs he was interested in.
Exactly. In particular, cut elimination goes through. Not without its problems. I mean, there are serious termination issues with cut elimination, and of course non-confluence issues too. But he was able to prove it for the classical sequent calculus, and it crucially, his method and all methods, I'm not sure I should say all methods, but the classical methods take advantage of the fact that you're dual, and that you have many formulas on both the left and on the right.
Oh, right. Yeah. So the key idea behind cut elimination here is that we don't have to do any guesses in our proof anymore, right? Like that's where the guesses come in, is when you do a cut. So why is there I don't know, a key intuition why using the sequent calculus allows you to prove this sort of thing so much easier?
That's a really good question. I think so. When you speak to a structural proof theorist, what do they do when they try to get rid of something? So there's usually a phenomenon like, say guessing or non-analyticity, it might be called, and you want to eliminate this phenomenon in your proof. So what they usually do as a structural proof theorist is they'll take the rule in question, the culprit. They'll take the culprit and they'll start trying to eliminate it. How do they eliminate it? Well, they do the only thing they can. They push it up the proof until somehow it disappears completely. But as they're doing it, they realize that they get blocked at certain points. So they then have to generalize that phenomenon so that they can go past that step. And eventually they get a general phenomenon that they're able to eliminate completely that subsumes the original phenomenon. And that's exactly what cut is. It's a generalization of modus ponens. So modus ponens is the fundamental non-analytic rule in your Hilbert-Frege system, right? It's A, and A implies B, infers B. Mm-hmm. And the problem is, if you're looking bottom up, you're trying to prove B, but you've got to guess this formula A out of nowhere.
Right.
And so you can think of just saying, okay, I've got a calculus, I've got introduction rules on both sides, or introduction elimination rules, but now I've got to deal with this modus ponens. So let's just try and eliminate it. And then immediately you get stuck on the first rule and you realize, well, I'll need a generalization of modus ponens that allows for some side formulas, not just A implies B, but, maybe some C and A implies B or D. And then you can cut the A against the A, and that's how you end up with a cut. And so the cut is just a generalization of modus ponens that's designed to actually play well, designed to be eliminable. And actually what Gentzen did is he actually had to generalize it further. So he generalized it to something called a mix, which is what he really eliminated. But there are proofs of cut elimination that don't require that.
So a mix is a generalization of a cut.
Yeah, it's like a cut merged with contractions on both sides. So if you think of a cut as gamma entails delta A on one premise, and then gamma A entails delta on the other premise, and that infers gamma entails delta, it's just having multiple copies of A on both sides. That's the mix.
Right. Wow. Right. No, yeah, it does make a lot of sense, because that's what we do in mathematics and logic all the time. It's like you have a precise problem, you want to prove it. How can we make our life easier here? Is we generalize the problem first. So
yeah,
in a sense,
exactly.
In a sense, we can think of sequent calculus as a generalization of natural deduction. Not necessarily it's an easier system to work with, but it's definitely an easier system to prove meta-theoretical properties and then translate it back to natural deduction, because there is a one-to-one correspondence.
And I should say that this is how I believe Gentzen thought about it. He thought of the cut elimination of the sequent calculus as a calculus for the meta theory of natural deduction.
Right.
I think it's really only after Gentzen's work that proof theorists started using the sequent calculus as the go-to calculus in its own right. I think it's gotten to. Yeah, I mean, now I think the sequent calculus is the main calculus of proof theory. I mean, and this is the one calculus that all proof theorists, I would say, know and should know. There are many proof theorists who don't really know natural deduction, I would say. But I think all proof theorists know the sequent calculus.
Right. Coming from a CS background, I just knew natural deduction, and I got my hands dirty with sequent calculus with you. So that's interesting.
Well, maybe I'm being biased. I mean, it depends what you call proof theorists, really. And I don't.
No, but yeah,
I don't want to be this guy who excludes certain people, right? So I'm sure if you're a proof theorist from a sort of type theory point of view, then of course natural deduction is much more natural to you, and there's not as much reason to know about sequent calculus. But so I started out doing some proof complexity, and in proof complexity, you talk about Frege systems, and then at a stretch, you talk about the sequent calculus, or maybe a Tate calculus. In the proof theory of arithmetic, actually, many people talk about things that are closer to sequent calculus than natural deduction. They're called Tate calculi, and I don't think many people really think about natural deduction there. I think proof sequent calculus is the most interesting thing.
Well, in a sense, we can also argue that proof theorists are interested in meta-theoretical properties, so it makes a lot of sense to use something more close to sequent calculus, right?
Yeah. I think methodological reasoning is much easier for the sequent calculus. So certainly, I mean, if someone asked me to go away and prove the consistency of arithmetic, I would turn to the sequent calculus immediately. That said, just recently we had this reading group in my group, and we went through the proof of the consistency of arithmetic in the Troelster-Schwichtenberg book, Basic Proof Theory, and they do it in natural deduction. And I was rather convinced from that exposition that actually the natural deduction proof was quite, was fine. It works fine there. I just wasn't used to it.
Okay, so you're saying basically, I don't follow much of what's happening in the proof theory world, but you're basically saying that you're looking into these different systems and different formalizations and doing the natural numbers meta-theoretical proofs in this system. What do you gain from that? Like, you're looking for the strengths of this particular system, and what's the research interest there?
That's a good question. I mean, so let's say, without getting into actual strength measures and stuff, some of the beginning motivations of proof theory were also coincided with the motivations of Hilbert's program. So we want to prove the consistency of, say, Peano arithmetic. Okay, so Gödel tells us that we can't prove it within Peano arithmetic.
Before we continue, do you want to give a brief explanation of Peano arithmetic, just in case our listeners are not familiar?
So Peano arithmetic. So broadly speaking, you can think of this as the theory of induction. So you have first-order logic. The language is just the language of arithmetic. So you have a symbol for zeros, a symbol for successor, addition and multiplication, and let's say inequality. And from here, you can write down, a lot of undergraduate mathematics can be written down in this language. Maybe not analysis, but certainly a lot of first-order number theory can be written down in this language. And the crucial axioms in Peano arithmetic are, okay, you have primitive recursive definitions of the symbols of, addition and multiplication in terms of successor and zero. But crucially, you have the induction axiom schema. And this says that from a of 0 and for all x, a of x implies a of x plus 1, you can infer that for all x, a of x. Okay, so is this the usual induction? And so I would say Peano arithmetic is really the first order theory of induction over the language of arithmetic.
It's, in a sense, it's the weakest system which we can do interest in mathematics, right?
No, it's not the weakest system we can do interest in mathematics. Okay. There have been a number of people who have tried to do it in weaker systems. I think famously, Ed Nelson wrote the Predicative Arithmetic, I think, or Predicative Mathematics, which is a book that tries to found much of modern mathematics in a much, much weaker theory. And of course, you have all these people now doing things like bounded reverse mathematics or even reverse mathematics, where a lot of mathematics is doable in much weaker theories. So I think you really have to search hard to find things that can't be done in the theory I sigma 1. So this is the theory of induction on semi-recursive predicates. So induction on things like the halting problem, right? And in this theory, it turns out you can well define all the primitive recursive functions and only the primitive recursive functions. So things that you can't prove in this theory are things like well-definedness of the Ackermann-Peter function. Things that you can't prove are you also can't prove things about like infinite combinatorics. So like the infinite pigeonhole principle or Koenig's lemma. These things that you cannot prove. But if you're doing some basic algebra, if you're doing some number theory, a lot of interesting mathematics can be done in a theory as weak as I sigma 1, or also primitive recursive arithmetic. So I think you have to do a bit of work to find things that can't be done in these weak theories. And there are people who work on this, like people like in reverse mathematics, who try to classify the strength of certain results in mathematics by the axioms needed to prove them. And their starting point is a generalization of I sigma 1 called RCA 0, which is still a form of primitive recursive arithmetic. And, like I said, this is the starting point because a lot of mathematics can already be done in RCA 0. So you start thinking about, interesting problems in analysis and infinite combinatorics that start taking you beyond RCA 0.
But then coming back to Peano arithmetic now, maybe we use Peano arithmetic because it's historical perspective then? Is it what we're used to working with?
One could argue that, but I think if you think but by the same argument, we study induction or we use induction and recursion because of a historical perspective. I think most of us believe that the status of induction and recursion is much more general than just convention. They seem to be quite natural things. So from a computational point of view, recursion is just such a natural way of doing some programming, right? It's such a natural feature of programs that, I think of it as something more than convention. And same with induction. So recursion and induction are two sides of the same coin. Induction is the logical counterpart of recursion. So as soon as you think that induction is a natural thing to study, then Peano arithmetic just falls out. Because it doesn't matter what the other axioms are. It turns out any choice of basic axioms that's sufficiently large all become equivalent once you add induction. So I really would frame Peano arithmetic as the theory of mathematical induction in first order logic over the natural numbers. Okay. So I think it's quite a robust theory for that reason. And there are books that talk about this sort of robustness. So I guess a well-known one is the Hayek-Pudlak book, Meta-Mathematics of First Order Arithmetic, and they sort of gloss over the basic axiomatization and they just talk about the things where it differs. So do you take induction as a starting point? Do you take minimization as a starting point? But really, it's the study of those principles of induction or of minimization or of replacement, these sort of principles. And so, where was I before this? If you want to prove the consistency of Peano arithmetic, then this is something that proof theory gives you. It gives you a way to prove that. So, what is consistency? It says there's no proof of false. So, what's one way to prove that a system is consistent? Well, a first attempt that the structural proof theorist might do is to just show cut elimination for the system. So suppose you had a proof of false and you have cut elimination. then you have a cut-free proof of false. But then, because cut-free proofs are analytic, by the subformula property, this proof of false can only contain subformulas of the formula false. But a direct inspection of the rules tells you that there can be no concluding rule here. No rule can have conclusion that's just false.
Right.
And then you immediately get consistency from cut elimination.
Wow.
Now, what goes wrong for arithmetic? Well, the problem with arithmetic is you don't have cut elimination for arithmetic because, it's because of something quite natural. You need inductive invariance. In everyday mathematics, we do use induction, and we have to make clever guesses with induction invariance. When you want to prove something, sometimes you can't just prove it directly by induction. You have to generalize the statement that you prove so that the inductive invariant holds. And those invariants are things that you fundamentally need to guess. And actually, via proof theoretic techniques, we can show that you really need those guesses. There's nothing you can do to eliminate those guesses. But what Gensen did, well, maybe he didn't spell it out in these terms, but it's maybe more apparent in Schutter's reformulation of one of his consistency proofs, is he shows cut elimination for a sort of infinite version of arithmetic. So he takes induction and he translates it to some omega rule. So he just unfolds the induction into infinitely many derivations. And then he proves the cut elimination in this infinite system. And the same argument works. You still get consistency. The only problem is he has to control this infinity using a careful ordinal annotation. And this is what leads you to require induction up to this ordinal epsilon 0, which is this famous proof theoretic ordinal of piano arithmetic. And you asked me what a proof theory is doing. Well, that result of Gensen essentially inspired a long line of research which tried to establish the proof theoretic strength of various important theories. And more importantly, a proof theoretic treatment, a proof theoretic analysis of these theories. That means have a constructive interpretation of these classical theories. So piano arithmetic, famously, we can interpret it into high-tone arithmetic by a double negation translation, which can in turn be interpreted into a really, really simple programming language like System T because of something like the dialectic interpretation or realizability interpretation. And so this line of work seeks to interpret stronger and stronger theories and to actually have a measure of their proof theoretic strength. So piano arithmetic, we have epsilon 0. This was, famously improved to even impredicative theories, where you have quantifiers over sets that may include themselves, right? So the something called pi-1-1 comprehension. And a famous result of 20th century proof theory is to get interpretation of this into predicative theories of inductive definitions. And so I guess one thing you can say in a nutshell is what's the biggest open problem in proof theory is to give this interpretation for second-order piano arithmetic. So second-order arithmetic, sometimes called the theory of analysis, we have no proof theoretic measure of this theory. Or we do have a proof of its consistency, thanks to Tate and also Girard and Spector, but we don't know what strength this uses. We have no idea what principles this is using. We don't know what ordinals we need to establish this consistency.
So can you repeat that? Which theory is this? The theory
this is PA2. So this is called second order piano arithmetic. So this is essentially defined almost exactly like piano arithmetic, but you add a comprehension axiom to define sets, and you have induction over the extended language. And this allows you, this language, because you're second order, allows you to. So when I say second order, I mean sort of two-sorted first order, really. But this glossing over that, this language allows you to talk about analysis because it allows you to talk about infinite sets,
right?
Which means you can formalize analysis inside it. So this is, if you wanted a theory that you can do all of undergraduate mathematics in, I'm pretty sure this can do it. I don't think you learn anything in undergraduate mathematics that can't be done in this theory. So this is really like the super theory that can do it all. And, the consistency proof of this exists, but we have no idea what it uses. We have no idea what sort of ordinals are required to make it consistent. So when I say what do I mean by ordinals, so what's the least ordinal that PA2 cannot prove well-founded? We don't know what it is, and we have no idea.
Wow, you just blew my mind in this last part over here. That is absolutely fantastic. It's nice to see that this seems like a very fundamental question in proof theory, but it's still open, right?
It's still open. So I should say, we have consistency proofs, but the methods used are entirely impredicative. So they're not so satisfactory. They're beautiful, of course. I mean, So this proof by Tate. So consistency for second order arithmetic reduces to consistency for second order logic, and consistency of second order logic can be established via a direct cut elimination result, which is exactly what Tate proved. So Tate proves cut elimination for second order logic using, I believe, the first example of this sort of reducibility candidate method, this logical relation method, right? Where you take the set of reducible proofs and you show that they're closed under certain properties, and then you show that all proofs are reducible, right? So something you may use to show that something like all simply typed lambda terms are strongly normalizing, right? So it's this sort of method. This was like the first time we saw these methods, and these methods were generalized by Girard, who showed strong normalization of the second order lambda calculus, and of course Spector, who gave similar results for system T with bar recursion. So we have these methods that we're using all the time, but we don't yet have a good proof theoretic treatment. And of course, what these people did, especially people like Girard, was they were motivated by these things, and they ended up developing new tools and new logics, like linear logic, for example, to try and decompose the problem further. And now these things have become separate research lines in their own, in their own right. And so proof theory is, maybe changing again. It's now much more structural than it used to be. So, you can say that we want to understand proof theoretic strength, but now the tools for it are very, very structural. It's about cut elimination and understanding the structure of proofs. And in the background, there's this whole question of identity of proofs. If you think of other areas of mathematics, you always have a good notion of identity, right? So the first definition of group theory is isomorphism, like when are two groups the same? The first definition in field theory is the same thing. When are two fields the same? We have a notion of isomorphism. And one of the big things that's become quite prevalent in recent decades is to develop a good notion of isomorphism for proofs. So we don't have like the fundamental isomorphism theorem for proof theory because we don't really know when two proofs are the same. And I think these questions are really inspired by this traditional Hilbert's program style question of understanding consistency strength and when things are consistent. And it's fascinating that reduces to this incredibly structural, almost philosophical question of when are two proofs the same.
Wait, you lost him a little bit there. You're saying that asking the question of when two proofs are the same is very similar to the question of its consistency.
I'm saying that the question of consistency somehow almost reduces to that. So if you trace the line of proof theory from early 20th century to modern times, the subject matter seems to have evolved. So most proof theorists are much more of a structural nature now. They study low-level structural proof theory, proving cut elimination, proving decomposition results for logics. But yet there's an unbroken line here between this and Hilbert's program, right? Or at least the quest to prove consistency of theories. The consistency reduced to cut elimination for complex theories reduced to substructural considerations, or a better understanding of proof theory at the low level. So to understand proof theory at the low level, we all want to have a good notion of identity of proofs. And so it's quite fascinating that just this question of trying to understand consistency, that you can really see it as being reduced in some sense, not in a formal sense, but reduced in the scientific level to this question of when are two proofs the same, a really fundamental, almost philosophical question.
That's one reason why I think homotopy type theory is very interesting. It's one of the big questions they're asking. When are these two programs the same, right? Like that's the fundamental question that is trying to address early on, right? With the univalence axiom in some sense. Maybe we can talk more about this next episode when we have Thorsten over here, because
he's certainly more qualified to speak about it than me.
Right. But I'm just trying to draw this parallel here now that we're going towards the end of the episode, that exactly the problem that you are posing here, that is the biggest interest in proof theory, which is when are two proofs the same, is one of the, I would say, the hottest, one of the most hot parts of type theory that's been worked on, which is homotopy type theory, right? Which is very interesting, very, very interesting. How about we already going towards the end of the episode right now. How about we start talking a little bit about your research interests? What are the cool things you've been working on recently? What makes you excited nowadays?
That's a good question. Slightly unprepared for this. I think Okay, so I'm not going to say about the individual low-level results that I've been doing, but I think I can say something that I think I said at the Midland Graduate School too. So I mentioned that Gensen had this idea of making proofs infinite in order to get consistency results. So, he started with pure arithmetic and he sort of unfolded the induction rule into this infinitely branching omega rule and then proved a cut elimination result for these infinite proofs. And then one of the developments in the last couple of decades that has become increasingly relevant in proof theory is this idea of non-well-founded proofs. So this is a different sort of infinite proof. This is an infinite proof that is finitely branching still, but can be infinitely deep. So a priori, you could admit fallacious reasoning because as soon as you have non-well-founded dependency, then you can prove false things. But one of the really cool things about the inception of this area is that it was motivated by results in automaton theory. And it turns out that you can impose certain conditions on these non-well-founded proofs that are, that stem from acceptance conditions for infinite word automata that guarantee that your proof is meaningful, or for logic that it's sound, or for a type system that you terminate. And this gives you access to a quite large class of well-behaved infinite proofs. But what's even cooler about this sort of infinite proof is that unlike Gensen's methods, where the proofs were necessarily infinite and had no good finite representation, I would say, non-well-founded finitely branching proofs do have a good class of finite subproofs, of finite fragments, which is what are called the cyclic proofs or the circular proofs. And those are the ones who have only finitely many distinct subproofs. So that means you can kind of write it down as a graph, as a directed graph, potentially with loops or cycles. And why do I think this is cool? Because I think this is something that was not very natural to do in the 30s when Gensen was around, but now is much more natural because of the inception of modern automaton theory. So this gives us sort of correctness conditions for these non-well-founded proofs, which means we can do some proof theory with them. And the proof theory for this has several nice properties. So like I said, we have this good candidate of a finite proof. And this good candidate allows us to develop even more metalogical results than we could before. So before, I said that cut elimination, or sequent calculus, one of the good things about this is that we can prove meta theorems. For example, a Bronze theorem or Craig's interpolation theorem, all these famous theorems. Well, we can't do that with these infinite proofs. We can prove some things like consistency, but not all things because of the infinite nature. However, with cyclic proofs, because they're finitely representable, sometimes we can. So there are many results now that try to use cut-free cyclic proofs to develop things like interpolation results for modal logic with fixed points. And so this is really cool that we can use this to get more metalogical results. On my side, I think that these non-well-founded proofs tell us more about the meta theory the meta mathematics of a theory than we could do with usual proofs. So I think this was already observed by Grisha Mintz back in the 70s or something, that non-well-founded proofs can be seen as a counterpart to non-standard models. So for each non-standard model, you can identify a class of non-well-founded proofs that identified with that model. I'm not sure he ever formalized this. I think this was always sort of informal in the background. It was in the air at the time. And this is why he developed his continuous cut elimination strategy. But I digress. I think one of the things that wasn't apparent at the time was this automaton theory stuff. So I think one thing that would be really cool right now is to build a sort of bridge to have some more correspondences between proof theory and automaton theory. And I think this is a question we can only pose like nowadays. We couldn't pose it before because we didn't have the tools to even pose the question. But could there be isomorphisms or correspondences between classes of proofs and classes of automata in the same way that we have isomorphisms and correspondences between, say, classes of proofs and classes of lambda terms? Like a proof system for minimal logic corresponds to a simply typed lambda term. And I don't think this has really been thought about that much because we didn't really have the ways to phrase this problem properly. But I think this is now emerging. And this is the sort of thing that's driving my research at the moment.
That is absolutely fantastic. That's wow. I would never expect that you can actually have, like consistent proofs that are actually cyclical and still make sense, that are actually non well founded. They're actually non well founded, you mentioned, right?
Yeah, I can give a link to a talk I gave actually on cyclic arithmetic.
Let's put that in the
And you can
links
maybe
on the description. I'll definitely also put the Stanford
Encyclopedia of Philosophy.
encyclopedia over there. So make sure to check out the links of the episode. We're gonna put a bunch of cool stuff over there. Well, we are almost 1 hour in. Is there anything else you would like to bring to our attention that we didn't have the chance to discuss?
Not really. I mean, you've asked me quite a lot of questions. I've given my personal viewpoint on things. Maybe I'll just reiterate that. On the historical stuff, I see things a certain way. I'm sure other people see things another way.
But yeah,
I think it's better to leave it there.
The way I look at it is like, yeah, it's a personal perspective, but in a sense, is a personal perspective of someone who has a lot of. You've been in the field for a while now, right? Like you have the rights to have your opinion. So it's opinion that, well, me particularly, I just started my PhD a couple of years ago, so it's something that we can learn a lot out of. Like maybe it's not the entire truth, maybe there's some pieces that are missing, but in a sense, we all learned a lot from you. Thank you so much for everything.
Oh, I'm happy to have participated, Pedro. Thanks for inviting me.
Yeah, thank you. I am looking forward for the next episode where we're gonna have a very nice discussion with Thorsten Altenkirch. We are gonna make that happen. So
I'm looking forward to this too. It should be lots of fun.
Thank you so much for coming, and I hope everyone enjoyed it as much as I did. Once again, I hope you guys enjoyed this episode. If you liked it, don't forget to leave a nice comment in our website, www.typetheoryforall.com. But if you really enjoyed it, don't forget to recommend it to a friend. Growth and engagement is the best way to keep us motivated to keep producing more and more cool content for you. Spoiler alert, in the next episode we'll have a real cool discussion of classical logic and intuitionistic logic with Anupam Das and Thorsten Altenkirch. Make sure to follow us on Twitter at p_Abreu0, because I always announce there when we have a new episode. I hope to see you guys next time.